above all else. So let me go ahead and start my... And the thing is that from chemical equilibrium, delta G, right, and our laws of thermodynamics tell us what reactions are feasible or even product favored. Right? Certainly they tell us that. That's what you guys are studying right now in homework 5. Right? The feasibility of a reaction. And of course delta G tells us something about that. It tells, however, delta G tells us nothing about the time scale the process takes place upon. At which the process takes place. All right, so delta G is negative for a process. We know that means it's product favored. It's going to go to products. It doesn't tell us anything about how long it's going to take. All right? Really, really simple calculation to do is to go take, as I've mentioned before, go take, and I think, no, you don't do this on the homework. Say take ethane, methane, or something like that, and calculate delta G for the combustion reaction, right? CH4 plus O2 goes to CO2 plus H2O. Balance it out. Calculate delta G at 298 for that reaction. It's very negative. It's very, very product favored, right? But methane doesn't go. Right? Methane doesn't spontaneously combust in front of you or your very eyes. It would be really bad if it did, right? Right? What do you need? You need a spark, right? You need some sort of initial kick to get it going. Okay? And then the equilibrium will start to kick in, right? And then we'll see lots of products, right? That methane, once it sparks, it goes, right? It's never going to stop, right? Because delta G is very, very negative, right? It's gonna combust the hell out of itself until there's no more methane left. It's very, very spontaneous and exothermic and entropically favorable, right? It's just going to go. But it doesn't until you do something to it, right? And that doing something to it, that kick you give it, right? Delta G doesn't tell us anything about that kick. There's absolutely nothing about it, right? But that kick is so chemically important because you've got to get that reaction going, right? And you've seen that, we talked about Haber-Bosch, the same idea. And H2 plus N2 goes straight to NH3 based on delta G at 298. It's very, very negative, right? Should be all completely product favored. But it's not. H2 and N2 just sit there like nothing, right? You need to put it through a catalyst at high temperature to get it to break apart, right? And that's that kick that the system needs to get going. That catalyst provides that kick, okay? And so delta G only answers half the question for us, right? It doesn't tell us anything about the necessary input of energy that we need to get the system going. Right? And that's a kinetics question. Right? It's a question of kinetics. The idea is that equilibrium, delta G tells us what happens if we let the system stay. I'll write this down. Delta G tells us the results of the process at infinite time. Right? If we let our N2 and our H2 sit in a container together, and we just let it sit there for eons, and I mean eons, eventually NH3 will form. It has to. Spontaneous. Delta G is negative. If there's ever a chance for N2 and H2 to react in that container, it will react and form NH3. But the fact of the matter is that the event, that reaction event itself, is so incredibly rare, and it has to be done at just the right enough energy to break those bonds, that it's basically impossible for it to happen. Right? And we can look at the kinetics of this process, for instance, but when we look at the rates, the kinetics for the Haber-Bosch process in the absence of a catalyst, what would otherwise take the catalytic process in problem set 5 only a couple of seconds would take something like 10 to the 18 seconds without the catalyst, right? 10 to the 18 seconds is like almost a lifetime in the universe. Not quite, but getting close, right? That's billions and trillions of years, billions and billions of years. Right? So it doesn't tell us anything about that, right? So delta G will tell us something can happen, but it doesn't tell if it's going to happen anytime within our lifetimes, much less during a lab period. Okay? Kinetics answers that question for us. And I want to try to convince you of that today. Okay, so that means that not only do we need to know delta G, but we need to know something about this time scale at which something happens, which we would call the rate of the reaction, right? So the key to kinetics, so we'll just kind of define it, chemical kinetics, and again, I will redefine this many times. Again, this is a very ephemeral, well, that's kind of a big word, kind of a nebulous term. Kinetics is a very nebulous term, and what an organic chemist will tell you about kinetics is very different than what I'll tell you. I'll try to give you guys some sense of those differences. Right, but in general, chemical kinetics is the study of the rate in time of which a chemical process occurs. Right? So, right, the idea is that delta G tells us something about energy flow from reactants to products. But the kinetics, right, the rate, tells us something about the time it takes for reactants to convert to products. And of course, kilojoules for energy. And for rate, we're going to measure rate in terms of per second, right? We're going to think reactions per second, if you will. In fact, it's going to be something like concentration. The units are going to be something like concentration per time, right? So the idea is how much time, right? The idea is you're going to gain, like, say, 0.1 mole of your product per second, right? That's going to be your rate. Concentration over time. Okay? We're going to realize that the concentration units will depend on our reaction. So there might be different amounts of concentration. And we'll see that, for instance, for a unimolecular reaction, when you only have one molecule, if reacting by itself, concentration disappears and it's just per time. Okay? But, well, anyway, we can adjust the units as we need to. But the idea is very simple, right? We're going to measure how much number density of our products is going to form as a function of time. All right, the way I like to tackle this problem is to just think of it in a very simple way, okay? And to come up with, using the energy tools that we've used so far, to come up with an equation or some idea of exactly how we can start to think about how things happen in time, right? I like to use a chemical motivation for this. And I think it's easier to look at it from the perspective of a reaction and then kind of build things up generally from there. Right, so let's consider a very simple reaction. Let me save this really quickly. Lecture section 1, number 23. Okay. All right, so I want to consider this reaction. This is a Dr. Trillo special. I'm going to take methyl bromide, and I'm going to react it with a nucleophile, a base. And it's going to do a nucleophilic substitution to form methanol and bromide ion. Right? Does anyone know what this kind of mechanism is called? Does anyone remember the name of this type of mechanism for organic chemistry? It's a special name. It's like the first reaction you learn in organic chemistry. I'm looking at you, G. If I wrote this down, will this ring a bell to you guys? No, it's not Grignard. It's SN2 reaction. Right?
Yeah. That's at the end of I'm an organic chemistry person.
This isn't at the beginning of Orgo 1?
No, that's at the end of Orgo 1. I was gonna. No, it was.
Am I just like in this entire bubble that things are taught differently?
You learn.
Where do you learn nucleophilic substitutions? So you should learn, nomenclature at the beginning, right? You do nomenclature and structure. You guys do stereochemistry in Orgo 1 as well?
Yeah.
Newman projections and things like that?
Yeah.
Yeah. Functional groups, of course. Yeah. And then you start reactivity. Don't you start with SN2 and SN1?
Yeah. Hydroboration. That's
and hydroboration? Yeah, okay. So that should be like week 4.
Exam. I don't know.
Week 6, right?
It was like the end of
Is it end of Orgo? Okay, all right. Well, anyway, it doesn't matter. I'm just curious.
That's what you said at the beginning, and all of us.
I'm sorry. I apologize. Yeah. So this is the first reaction. I'm thinking nomenclature takes about a month, and stereochemistry another 3 weeks. Think about midterm was when you learn SN2. Okay, but anyway, let's remind ourselves what an SN2 reaction is. I'm just going to write. I'm going to draw the mechanism to it, and right. We're going to do electron pushing. I'm not going to do very much electron pushing in this class because actually I kind of despise electron pushing. But it's useful here to think about how it works. Electron pushing does not give you any real information. It's not a real. It's just it's a mnemonic. It's a learning tool. Don't tell any organic chemist I said that; they're going to be mad at me. But all right. So the mechanism works like this. I'm going to draw my methyl bromide very precisely because I need the precision. All right, remember in an SN2 reaction, the nucleophile, it happens in one concerted step. So the OH does a back attack, right, on the carbon, and we form an intermediate. Well, it's actually a transition state, which is a word I haven't defined yet, where an intermediate state where the OC bond is starting to form. You pyramidalize the carbon slightly so it becomes somewhat planar, and the bromine begins to leave. And I'll get that double dagger means transition state. I'll again define these things again later. And we're left with O on the opposite side. And the bromine leaves off like this. Okay, so that's an SN2 reaction. There's another way to do this reaction. There's a competing mechanism. Let's just remind ourselves what that looks like. And then we'll decide which one is probably the correct one. What's the other form? It's called SN1. And SN1 is a 2-step reaction. So I'm just going to write it like this first. The first step of the reaction is the system ionizes. So we form a CH3 cation and a bromine anion. And then the negatively charged OH comes in and attacks. Like this. And we're left with CH3OH plus Br minus. Right? Same result, same outcome, but slightly different process. Right? Here we have, right, there's no charge formation here. But in this case, we have ionization, at least temporarily. Okay, so that's the difference between the two. They work in 2 different steps. They actually have different kinetics. That's why we call them 1 and 2. Do you guys remember that? Why they're called 1 and 2? 1 is because this is only dependent on the kinetics are only dependent on the concentration of the bromide. In SN2, it's dependent on the concentration of both the nucleophile and Br. So So this means that the kinetics are dependent on two concentrations, means it's on one. All right, well, we'll go back to this and look at those things more carefully, but there's a difference. But these are competing. Does anyone remember which one is preferred for a primary alkane or a primary alkyl halide? Which one is preferred? Does anyone remember the rules?
Isn't it only tertiary that's preferred for SN1?
Say it again.
Isn't it only tertiary that's preferred for SN1?
Correct.
Yeah.
So typically, SN1 is preferred by the species whose cations tend to be stabilized, and so tertiary carbons tend to be the ones that do that. All right. Right. So this reaction doesn't. Basically, this never happens. All right. SN1 doesn't happen. CH3 plus is a very unstable species. All right. And so if this were a T-butyl group, for instance, right, where you have instead of hydrogens you have methyl groups, this would go through SN1. Right? So this is an SN2 reaction. It only goes through SN2. All right. Now here's the next question. Another organic chemistry test. Is this reaction, I haven't specified this, right? This is an equilibrium. Right? I should always write that this is an equilibrium. Is this product or reactant favored? The organic one knowledge should be able to answer this question. Does anyone remember what determines the product favoredness of a SN2 reaction? What the characteristic you need to look at is? Anyone have any ideas about this? Think about the leaving group. If the BR is leaving, what does the leaving group need to have relative to the nucleophile in SN2 for it to be product favored? Does anyone remember?
Electronegativity?
Well, electronegativity might be fair. I'm not sure that's going to get us the right answer. But rather, let's think about this in terms of an equilibrium, like an acid-base equilibrium, for instance, right? Right? We have two bases, bromide ion and OH anion, right? So we have an anion on the left that's OH, which is a strong base, and what is bromide? Is bromide a strong base or a weak base? Weak base, right? Because HBr is a strong acid, right? So we have a weak acid, weak conjugate acid, strong base, and we have a weak base and a strong conjugate acid, right? On your product side, which is preferred? A weak base or a strong base? Weak base, right? Because if it were a strong base, it would just go back and react again and go backwards, right? So this is product favored, right? Very product favored, right? Because Br is a weaker base. Right? So I should really write this like this, right? Like that, right? Very weak like that. Okay. So this is a little organic chemistry, right? So at least we know how this reaction goes, right? This is product favored, then it goes through this single step reaction where the OH comes in at the same time the bromine leaves, right? One step. Right, so let's think a little bit now about how does the energy of this system, so think about the energy of, say, the Gibbs energy of the CH3Br and the OH come together, the sum of the energy, and how does the energy change for this combination as the system reacts? Okay? So how does the potential energy or the potential energy of the system change as the bonds are breaking and forming? Okay? So we're going to start thinking about this in terms of energy. So here's a really nice way to think about this. Right, so let's analyze exactly what's going on here, right? In order for this to happen, we need to break the CBr bond, and we need to form a new OH bond. Okay, so what I'm going to do is I'm going to think about tracking the energy of this reaction as a function of these bond lengths. Okay, so we'll think about at every point along the reaction, or every point along these distances, at a given distance, what's the energy of our complex, right? So at the beginning time, we have a really small CBr bond and a really, really long CO bond. Then there's this period where they're kind of intermediate, about the same. And then at the end, we're going to have a situation where we have a CO bond that's really small and a CBr bond that's really, really big. The bromine's really far away. we're going to think about how the energy changes as those bond lengths vary. Right, because that's basically all that's happening in this reaction. The other thing that's happening is this carbon is rehybridizing from one side to the other. Right, we're not going to worry about that. That's a smaller part of this energy. Right, where it's really the bond breaking that we have to think about mostly. So let's think about this reaction from the point of view of the bonds. Okay, well, what if we treat this molecule like a diatomic molecule or a Lennard-Jones molecule, right? We treat the distance here between the C and R as R. Okay. And we can model this is a concept we're going to learn next semester, so I'm just kind of introducing this here. We'll talk more carefully about it next semester. But we can model the energy, the potential energy of this bond approximately. It's all approximations. With a so-called Morse, M-O-R-S-E, it's named after a man named Morse potential. Right, this is a function that we often use to model the energetics of a bond as we stretch it and break it. If you guys remember back in a long time ago, when we talked about real gases, we talked about the Lennard-Jones potential, right, and how that allows the atoms to attract each other. Okay, so the Morse potential is a lot like the Lennard-Jones potential, but it's built for covalent bonds. Okay, so it's more of a covalent model for how a bond functions covalently than it is these weak interactions. But as you'll see, it looks very similar. And this function, and we'll talk about why we use this function next semester. It's not that important right now. Just know that we can model these things with a function. And it has an energy. You can write G if you want instead of E. It's equal to this number D sub E. I'll define all these in a second. 1 minus E to the minus alpha R minus R sub E, all squared. All right, so there's a couple of numbers that we need to define here, and I'll define them for you in a second. As you'll see that these bonds, remember in a Lennard-Jones potential, there were two parameters. There was the attraction, the weld depth, how deep the attraction is in terms of potential energy, and also the length scale of the attraction, right, which is like the bond length, if you will, okay? So this, as we'll see, this is the weld depth, the attraction between the two atoms, the maximum depth of the potential energy, and R sub E is the bond length. And then alpha is a parameter that determines the shape of the potential. I'll show you those graphically. So if I were to plot this, we plot as a function of the bond length, right, which is the carbon-bromine bond length, and we plot the energy as a function of that bond length. You get a curve that, again, looks a lot like the Lennard-Jones potential, like that. Okay. And it has a negative energy from this perspective. So what we're saying is that the energy of the bond at infinity is 0, right? There's no interactions between the Br and the carbon at infinite distance. This energy, which is the minimum energy of the potential, is D sub E minus D sub E. And the bond length at which the energy is minimum is R sub E. Okay, so this just tells you again where the bond likes to be. Right? We can calculate the carbon-bromine bond length if we want. It doesn't matter here. And it's got some strength, right? D sub E is the strength of the bond. Another way to think about D sub E is it's the amount of energy you need to put into the system to break the bond. Right? D sub E, right? So this D sub E is what's called the dissociation energy. Right? It's the amount of energy to break the bond.
Can I ask a question?
Yeah, go ahead.
So, like, I'm a bit confused because I don't see how the graph like shows that. Because like, when you're saying the energy is going negative,
Yeah.
like, could you describe it?
Sure. Well, think energy equals 0 is where there's no interaction. The atoms are at infinite distance. They don't talk to each other, right? So E equals 0 is basically no interaction at all.
So there's also that when they're really close. Like, that confuses me. Then, 'cause
So as they start to come close, at long distance they start to attract each other, right? Because you have they should attract each other. Right? You have an electronegativity difference here, right?
well, if you have a very low R though, then don't you also have like there's a point where it crosses over?
Yes, that's right. The point is that when the atoms get too close to each other, they start to repel. Because the electrons in one repel the electrons in the other. So at long distance, they don't talk to each other. And then there's some intermediate distance, which is the bond length, where the energy of attraction is maximum. Right? That's obviously where the bond wants to sit, right?
Okay.
Right? And
Thank
so
you.
that's this point. And if you crunch the bond more, it's going to raise the energy because the atoms want to repel and stretch out again.
Thank you.
Does that make sense?
Yes.
Okay. So this is the repulsive wall, if you will. I'll write that in a second. Right? This is where the electrons of the atoms now, they want to push away from each other, right? Because negative charge and negative charges don't want to be too close to each other, right? So there's like this Goldilocks region where the bond forms, where everything is kosher. But if you go past that, the energy rises again. Right, so this is the repulsive, close touching repulsive wall. Atoms can only be so close to each other. Okay, so when HBr, sorry, not HBr, when methyl bromide is just hanging out by itself, right, just sitting by itself, relaxing, not doing anything, it's sitting right here at the bottom, right? Roughly. Right, the idea is that this point right here, right, what we call this point, R sub E, is what's called the equilibrium bond length. Right? So if the molecule is allowed to sit by itself and it's not being perturbed by anything, and it's just relaxing, that's where it's going to sit, right there at the bottom of the well. Remember, chemistry, chemicals, molecules, everything, they want to be as low energy and as lazy as possible. So they're going to always find the lowest energy spot they're going to want to sit at, and they're going to stay there. Right? Always at a minimum. Okay? So again, CH3Br looks like this. Okay? So if, imagine now the reaction, the OH comes in, right? OH comes in, we're going to have to take that CBr bond, and it's going to have to stretch to leave, right? So we're going to have to put in some energy into our bond in order to break it. Right? But the idea is that the OH bond, that the O and C bond that is forming at the same time on the other side, is providing the opposite effect. Right? So as the CBr bond destabilizes and it starts to stretch, the CO bond is going to be going the opposite direction and start to go towards equilibrium. So as one rises, one bond's energy rises, the other one falls. Right? So there's this balance of energy. The OH is going to provide some stabilization to offset the destabilization of the bromine. Right, so let's think a little bit about how to draw this this graph, but to include the oxygen as well. Right? Because we have two bonds, one bond breaking, one bond forming at the same time, and both bonds kind of have these same potentials. So imagine that I'm actually gonna take this figure and put it on another page because I need a little space here. So let me copy this over. Actually, how much space do I have on this screen? Not enough. Okay. And I'm going to erase all this right here for now. So I want to use this picture. So this is our, we'll call this our CBr bond. So this represents CH3Br. All right, and on the same scale, I'm going to draw the potential for the OH. Now, one thing that we know is that the Gibbs energy of reaction is negative, and that means that the energy of CHOH plus Br minus is less than the energy of CH3Br plus OH. Okay, so if I draw a potential for the OH bond, that bond is actually stronger because the energy is lower. The molecule, when it sits in the OH bond well, it's even deeper. Right? So what I'm going to have to do is draw an offset and draw the minimum of my OH potential lower. So imagine that I do it like this. I'm just going to kind of show you in kind of a schematic way. So let me draw my, sorry, that was a bad picture. So let me go ahead and draw like this. This is going to be the COH side of my system. And I'll draw with a different color. At long distance again, the system doesn't have any interaction, and then there's a stabilization. And it goes deeper than the Br because the bond is stronger. And eventually it starts to rise up like that. Right? So this energy difference, if you will, let me draw some lines here. The energy difference between this point, and let me draw it very carefully here, this point, which is CH3OH, that energy difference is just the difference in, is just the delta G of the reaction difference at this condition. Because I've broken a weaker bond, CBr, and I formed a stronger bond, COH, and so the energy naturally has to drop after that process, right? So this minimum has to be lower energy than this one, right? This is what delta G means. That I've taken my system from a one minimum at some energy and put it in a new minimum at a different energy. Okay. So what happens now when this system moves from Br to OH, right? So as I start, let's start from here and then we'll put it there, right? So as I start to do that, so at this point right here, the Br is very close to the C, and the O is very, very far away. Right? The O is very far away. So I'll kind of draw it right here for you. All right, we have just a regular old CH3Br here. And we can just kind of say that the OH is like 1,000,000 miles away, right? The OH is here at this point. Right? And then the system basically progresses, right, up this hill to react. And that Br bond starts to stretch, right? So so CBr gets longer. Right? So I'll just write plus, right? CBr gets longer. And COH gets smaller. Right? And eventually there's this cusp right here where the energy kind of flattens out. We're kind of in this intermediate point right here. Right? And so that would mean that, again, we're kind of at this place where the destabilization of the bromide bond from breaking it is being compensated exactly by the formation of the OH bond. Right? At this point, they're basically the same energy. COH is the same as CBr. Right? They're still kind of far apart from each other, but they're balanced. Right? So there's this magical point in the middle that kind of looks like this, where The OH is really close, but kind of far, and the bromine is kind of far. And then as the bromine continues to leave, right at this point, again, CBr is increasing in distance, and COH is decreasing in distance until the system comes back down and eventually equilibrates right here at this point. Right? And that point, of course, corresponds to R sub E for the COH bond. And the complex of the system looks like CH3OH. Let me write it differently, sorry. I just need some space. And the bromine now is really far away. Okay. Well, this is our mechanism, right? So now what I've done here, this is very interesting. I've now correlated the energetics of this reaction, delta G, to structural changes in my molecule, right? I'm watching the energy change as a function of the position of the atoms. There's a very special name for this. So these curves, I'm going to do a different color so it's not obvious that let's do red. So these curves here, that's a terrible arrow. I'm sorry guys. So these curves are here called what's called a reaction coordinate diagram. We have a more specific name in physical chemistry. So we'll call this the scientific term. So an organic chemist would call this a reaction coordinate. It's a very reasonable term for it. But in physical chemistry, we call these real objects. A reaction coordinate is kind of like a mnemonic diagram, right? It's a visualization of what's going on with the energy and the positions of the atoms, but it's not really quantitative. So we have what's called a quantitative version of it. The real surface or coordinate is what's called a potential energy surface. Right? A potential energy surface is a function that, as a function of all the coordinates of your atoms, gives you exactly the energy of that system. All right? So I plug in, hey, my CO bond is this, my CPR bond is this, my hydrogens are in these positions relative to my carbon, and I get an energy out. Right? And a real potential energy surface is parameterized across all the coordinates of the molecules, right? All of them, including the hydrogens, the angles, the dihedrals, the positions. You can imagine that bromine maybe could come in at an angle instead of on the axis of the bond. It can come in at an angle. That's going to have a different reaction pathway, different energies. And so potential energy surface will tell you all of that information. You can calculate them. Right? People spend their entire careers calculating these surfaces where they can say, hey, as a function of every atom's position, I can tell you exactly the energy. Right? And so you can actually map out how a reaction moves through a potential energy surface by modeling these surfaces yourself and finding the right paths through them. Right? We'll talk a little bit about what the right path through a surface is, what a reaction actually is. Right? We'll come back to that. Right, but the idea is that ultimately, if I want to know everything about a reaction, I need to know the energy of my molecules as a function of the positions of the atoms. And so the potential energy surface might suggest there are multiple ways to form our products, right? There's the SN1 path. The potential energy surface will show you there's a path or a coordinate through the surface, energy, where you ionize the atoms, and then the OH comes in and just connects to the positively charged carbon. But that's not preferred because that's not the easiest way to move from point A to point B. There's a cheaper and energetically lazier way to do things, which is the SN2 path. All of these paths are perfectly accessible to the molecule. It can take any of them. But a molecule will only ever take the path of least resistance. So if we know a potential energy surface, if we know exactly what the energy of our molecules are at every coordinate, right? Atoms are this far away, this close, this way, that way. We know the energy, we can measure it, calculate it. Then we can measure exactly what the path of least resistance is from A to B. And I'll show you some examples of that this module. All right? So just kind of introducing some ideas. All right, so again, this doesn't tell us anything about the time at which things take, right? I'm just basically giving you a different way to look at the energy, and I'm projecting the energy on the coordinates of the atoms. Okay? It still doesn't tell us anything about time. Okay? So we have to figure out where to get time here. All right, so I want to now explain to you how that comes out. So this is our magical reaction coordinate. So let me just redraw it, kind of a simplified version of it, just to keep things simple. All right. Let's just redraw it. A more simple diagram. Right, so we'll call this zero energy. Right, and we'll define it so that the energy of CH3Br is exactly 0. Okay, we're just rescaling our energy so it's 0. And the curve again increases until we reach this cusp. Let me actually get it so it cusps at the right temperature, right point. This. And then the energy decreases like this. And then this point right here is CH3OH plus Br minus. I'll add the OH minus here. Okay, so this is kind of a basic diagram. Okay, and so let's imagine now we have, right, we're going to put our CH3Br in a pot, in a flask, and we're going to heat it up, right? We got to equilibrate it at some temperature, right? So let's equilibrate it. So the first thing we're going to do is equilibrate our sample in a NPT, right, number, part pressure, temperature constant bath. Right, we call this the Gibbs bath, right, which means that we have a well-defined temperature. All right, and we'll just set pressure to 1. All right, doesn't matter. Pressure doesn't matter here. Okay, so if we're at a given T, the average energy, which is let me rewrite it. So this is average energy. I always wrote this as E bar, average energy, per motion is equal to 1/2 RT. Okay. So how many motions are there in CH3Br plus OH? Okay. So how many motions are there? Well, we can think of it a couple of different ways, but maybe the best way to think about it is that there are n atoms, each with 3 degrees of freedom, right? They can move x, y, z. So the number of motions is 3n. Okay, so the average energy of this system at a given temperature is 3n over 2 RT. Okay, so in this system we have 4, 5, 6, sorry, I can't count. 4, 5, 6, 7 atoms, right? So we have 7 atoms. Right, so the average energy of this system, of our molecules, is roughly 21 over 2 RT. Okay. Now, I don't really know, right? I don't have an energy scale here, so I don't really know what this point is relative to RT, right? But let's say it's larger than RT, okay?
Nice question.
Yeah, go ahead.
Why is n equal to 7, or is that just an example?
Because there's 7 atoms. C, right? There's a C, H3, that's 4, 5, 6, 7. 7 atoms. Right? You think each atom can move individually in 3 different directions. All right, so I'm going to mark, we don't really know what this energy is here because I haven't really defined it. So I'm just going to call it E double dagger. Call that little double dagger, little sword, 2 hilts. Or we'll just call it that. And let's assume that the average energy of the system is less than E dagger. Okay, let's just assume that. We can always change that assumption by just increasing the temperature. Okay, so what does that mean? Well, that means then that on average, the energy of the molecules is not at the minimum, but the average energy of the molecules is going to be right here. It's going to be at some positive energy. So this right here, we'll call this delta E, or delta G. Let's use delta G. Okay, and then this molecule, this region is also at some energy, delta G plus average energy. Okay. So really what's happening is our molecules, they aren't sitting here and here because we've heated them up. And so they're actually sitting kind of at this energy instead. Okay. Right. So you can imagine as the temperature increases, the energy of my molecules slowly creeps up. All right, so what does that mean? Let's imagine now. So let's assume something very, very simple, and this turns out to not be the best assumption, but it'll work here. Is assume molecules are basically like classical billiard balls. Okay, so what that means is that they roll along the surface. Right, so what that means is that on average, my CH3Br is sitting somewhere at one of these 2 points. Right, this is these positions. I'm not going to let me put it somewhere else. Right, so the molecules at this energy, on average, when you spot them, they're either here or here at this energy.
Can you explain that a little bit? Like, I don't see why they wouldn't be just at, like, why would they be there and not, like, at the lower energy?
Well, okay, so, right, that's a great question. So the only reason why they would be at this point is that they have no additional energy in the system. But I've added thermal energy to the system, which increases the energy of the molecules by 21 over 2 RT. And so therefore their energy now is going to be at this point on the Y, and the molecules as billiard balls can only exist at these 2 points on average. It's on average.
And you said it's because there's
Average
because of the
energy.
thermal energy.
The average, yes. So when you include the molecular energy, the energies of the bonds, the potential energy, plus the thermal energy, the molecules are on average at this energy. So when we look at the molecules on average, their bonds actually aren't going to be here, but on average we're going to see it here or here.
Okay, thank you.
Okay.
Can I also ask a question?
Yeah, please, go ahead.
In the yellow, the coefficient for RT, is that say 21?
It's 21, yes. Sorry, it's poorly drawn. Yes. It's 21 over 2. Okay, so let's imagine again that the ball on average is rolling, right? The ball has some energy, so it's rolling in this potential well, right? Think about it just kind of rolling back and forth like this, like a spring, right? What needs to happen for the molecule to react? Well, the ball needs to roll enough that it rolls over the edge and falls down to the other side, right? So in order for this reaction to occur, this ball, right, needs to have enough energy to get over that hill and roll down. Right? So therefore, molecule needs at least, right? It needs to have at least E double dagger energy. Right? Because if the molecule has this much energy, it's sitting right here at the cusp, and all you got to do is just give it a little poke, and it rolls down, right? Just got to give enough energy to get over that hill. Right? So that means that the molecules at minimum, E double dagger, in order to react. Everyone agree with that? Seems reasonable, right? Think about a ball, right? Imagine you're standing up here, somewhere you drop the ball, the molecule rolls, right? If you don't push it enough, it's going to come up here, it's going to roll right back down, and eventually lose energy. But it's not, there's no friction, it's just going to roll forever. But you have to give it enough push, right? If you give it enough push, it'll have enough energy to sneak up over the hill and then roll back down. Okay. So we have to have at least this much energy in the molecule. I'm sorry, we at least have E star, E double dagger, to get over that barrier. Okay. So now the question is, right, remember we have our molecules are random, they're in a statistical mixture, which means some molecules have more energy than average and some have less. And we have a formula for that. Right, so what we need to ask is, what percent or what number of molecules at T have energy greater than or equal to this E double dagger, the critical amount of energy that we need? Okay. Well, we have a formula for that. Right? The probability of finding a molecule with energy greater than E, circle. Right? We want to find the probability, right? Think about this as this is the probability of finding a molecule with energy greater than or equal to E star, or E double dagger, is equal to the Boltzmann equation. So this is going, well, let me just say this. Let's just say, actually, let's start here. Let's just do equals for now. This is going to be E to the minus E double dagger over RT. Right? This is the Boltzmann equation. Right? We derived this 1.5 million years ago. Boltzmann distribution. Okay. So the amount of molecules, right? The amount of molecules is an exponential function, a decreasing exponential function, so only a small fraction of molecules will have enough. But as temperature increases, this exponent gets smaller, and therefore this number gets bigger. So as T goes up, there's going to be more and more molecules with the right amount of energy. And that energy depends on the ratio of the amount of energy we need divided by RT, our thermal energy. All right, so that tells us exactly how many molecules have that energy. So now what we want to do is calculate the amount of molecules that have not only that energy but maybe more, right? Because if they have more than that energy, then they're just going to roll over. And that's going to be the integral from E double dagger to infinity of E to the minus E over RT dE And this equals to 1 over RT, e to the minus e double dagger over RT. Right? I didn't do the algebra out. But the important thing is that we get out of this is that the probability to find a molecule, which is proportional to the number of molecules, if we take this probability and multiply it by the total number of molecules in our system, we get the number of molecules that have energy at least E star, E double dagger, is proportional to e to the minus e double dagger over RT, the energy ratio of thermal energy, like the Boltzmann equation. So what that's saying is that if we have these molecules bouncing back and forth, the probability that they're going to react has something to do with the temperature that they're at and its ratio to the amount of energy that's required.
Can I ask a question?
Yeah, please.
So why, this might be silly honestly, but why wouldn't it be negative 1 over RT? Because like, if you're plugging in infinity, right, I see that would go.
Because you get because of the fundamental theorem of calculus, you get the integral evaluated at this minus this.
Mm-hmm.
That negative sign comes down, but there's a negative sign because you're taking this minus this, so it's minus 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 times minus is plus.
Thank you.
And probability can't be negative, right? So it has to be
Yeah.
positive.
That makes sense.
Yeah. Because that integral evaluated at infinity is 0.
Yeah.
So it's 0 minus this, and so you get plus this. Okay. So this tells us that every time that, basically this is the probability that every time a reaction event may occur, this is the probability that we have enough a certain number of molecules, the probability a molecule reacts. So if we have a molecule with sufficient enough energy, this is the probability that when it does react, it will react. And it's proportional to this energy, E star. Okay, so let me just summarize that really quickly. So let me take my picture from the previous page. And let me just summarize what I just said. Okay, so the probability that a reaction occurs is proportional to e to the minus this e double dagger over RT. Okay? But this doesn't tell us anything about time. Right? This just tells us something about a probability. Right? But the question now is, of course, you have to ask is, well, what do I need to do to think about this in time? Well, let's think of it again like the reaction extents from equilibrium, right? Put our reaction on a metronome. Every click, there's a possibility that the system will react. All right, so I click at some temperature, and the probability that a molecule will be in the right energy to react at that click is proportional to this, on average. Right, that's the probability that on a click that it'll react. Right, so all I need to do is take this probability and multiply it by the number of clicks per second. Right? How many chances does this system get to react per second? Right, so now let's do this, right? So now let's say, right? So now let's define the, let's think of it like the number of reaction attempts per second as this constant A, which has units of per second. Okay. So again, this is kind of, think of it again like this is the reaction metronome frequency. Okay. And therefore, we can say that the rate of reaction is equal to the number of reaction attempts times the probability reaction will occur times the probability reaction will occur per attempt. And that is as simple as rate is equal to A e to the minus e double dagger over RT. Okay. We define this rate, so more formally, we define what's called the rate constant, little k sub r, is equal to A e to the minus e double dagger over RT, right? Where k sub r is called the rate constant, right? This is what's called the prefactor, and this E double dagger is what's called the activation energy. Okay. So the rate depends on how many chances per second you get for the reaction to happen. All right, we're going to have to define that more carefully, and we will. And it's not really clear exactly what that's referring to, what defines the number of chances. But we'll have to think about that more carefully. And then this activation energy, which is this intermediate energy, right? It's the height of the barrier of this reaction, right? It's how much energy our reactants needs to get over this barrier in order to react. Okay, and what is that activation energy proportional to? Well, we described it here, right? That this high part of the barrier here is where the CBr bond is kind of broad, long, and the COH bond is kind of long, right? It's this intermediate region. Right? And so this activation energy has something to do with the strengths of the bonds, right? It has something to do with how much energy it takes to break one bond and how to break another, form the other, right? It's a balance between the two. So this number has something to do with bond energy, how much energy it takes to break a bond. Okay? That can be a big number. And we'll look at those numbers more carefully in following. Now, we're going to quantify all of this stuff, right? We're going to look at different cases, okay? All right, so in order to measure the kinetics, right, we need to be able to measure this activation energy and also this prefactor, okay? Now, for this reaction, well, we can look up the activation energies. Maybe we'll do that next class. Let's think about A for just a second, right? So one of the ways that I like to think about A in this case is that basically that this system is basically a bond. The Br bond is going like this, right? So it's vibrating like this, all right? And the more energy you put into it, the harder you're vibrating. And eventually you vibrate it so hard it breaks. So the question is that maybe A has something to do with the frequency, the rate at which this bond vibrates. That's a reasonable approximation, right? So let's look at those numbers. Let's see if we can get a sense of how big A is. Right, so let's think of A as kind of basically the frequency of the CBr bond vibration. Right? Basically, think of the CBr bond as a spring that is being stretched and relaxed. All right? You stretch a spring, think of it like a big slinky that you stretch really far and you let go and it bounces back and forth, right? Like a spring. All right, we'll look at these. You'll look at these springs next semester, you'll be sick of them, I promise you. We'll be thinking about this a lot. We can look that up, right? You can get this information from, or at least some estimate of it from infrared. So let's go look at methyl bromide's infrared spectroscopy. Look at the CBR stretch for methyl bromide. Infrared spectrum of bromomethane. Right, CBR kind of appears, let's say that's about, let's just make it easy, let's make it like 600 wave numbers, okay? Right, so the energy of this, so the energy of the CBR bond, let's just say roughly 500 wave numbers. Right, and now I need to convert that into time. Remember, so if you don't know, wave numbers is a unit of energy for light, and if energy's light is proportional to its frequency. So this number tells you something about the frequency of the light, and or the frequency of the vibration. Right? So I just need to convert that into per seconds. That's a calculation that we'll learn in the second semester. But the idea is that again, we're just doing spectroscopy. Wave numbers are the same as wavelength or frequency. You can always interconvert between them because it's all light. So this turns out to be about, I'll convert it myself. So it is 500 divided by 29.979. So this is about 16 times 10 to the 9 hertz, or per second. I'll just write it per second. Hertz. Hertz is the same unit as per second. So that's about 1.6 times 10 to the 10 hertz. Okay? So what that says is that if we think about the reaction only occurring when the bond is reasonably stretched far enough that it can fall apart, the rate at which it gets to that point is roughly proportional to the vibrational frequency of that bond. And that frequency is about, what is that, 10 billion, 16 billion times a second. All right, so our claim, therefore, would be that A is somewhere on the order of 10 to the 10. And that gets you to within about a factor of 100 or so of the actual answer. It's usually about 10 to the 12. All right, so the idea is that these things that, as we'll learn, and we'll really learn this next semester, that molecules are constantly vibrating, they're constantly moving, and they move at very specific frequencies. And those frequencies will define exactly how fast things will fall apart. Because again, what's happening is if you think about the bond as, or the molecule as a ball, or the bond as this string that's vibrating like this, it's only ever going to, the metronome's only going to click when that bond is perfectly stretched enough that it can fall apart, right? But its energy is high enough that we've stretched the bond far enough that the energy is above the activation energy. Right? And that's only going to happen every time the bond is stretched. And the bond is stretched roughly 10 to the 10 times a second. And we'll find that these A's, something like 10 to the 10, for things that are roughly 100, this is a reasonable number. This is within a factor of 100x of the real number. Now 100x sounds pretty bad, but we're dealing with exponential quantities here. So 100x is not bad at all. We're actually doing pretty good. And it's about 10 to 100 times the x. It's a reasonable guess. It's reasonable. Very reasonable. Okay? So what's happening is these molecules are constantly bouncing around. They're constantly reacting very, very quickly, right? This is like on the order, right? The period of this vibration is on the order of maybe 100 femtoseconds or a couple picoseconds. Right? These are oscillating rapidly. Right? And so there's lots of chances for the molecule to react. You would think it would just fall apart immediately, right? But the problem is that the activation energy might be really high. And that's exactly the problem with the Haber-Bosch process. Is that the Haber-Bosch process, again, these bonds vibrate very, very rapidly. But in order for Haber-Bosch to go, you've got to break 3 H2 bonds, 3 hydrogen-hydrogen bonds, And you've got to break an N2 triple bond. The activation energy for that is massive. So even though these atoms are vibrating rapidly, A is large for the Haber-Bosch process. E double dagger is very, very, very big. And so this number is infinitesimally small. And so the rate is tiny. Right? As I said, the rate's on the order of 10 to the minus 17. Right? So if this is 10 to the 10, this means that this thing is about 10 to the minus 27. Right? Very, very slow. Okay? So the activation energy is the most important part of the reaction. All reactions, the metronome for reactions are very, very fast. But the activation energies can be very, very large. And they slow the rate down exponentially. Okay? So we'll see that next class. We'll look at this more carefully and think about the balance of these two things, and we'll see that again. Activation energy plays the biggest role of them all. All right, guys, have a good one.
I looked at that one.
Me too. Thank you.
You looked